Hello guys, welcome to my YouTube channel. In this video, we will talk about the assumptions that we have for linear regression algorithm. Okay, so I have listed down the assumptions here. So we'll just read it once and then we'll go into depth one by one. Okay, this is also an important interview question. It has been asked in a lot of interviews lately. So please watch this video till the end to have the complete understanding. Okay, so let's start. So there are mainly 5 basic assumptions with respect to linear regression algorithm, and those are the relationship between the dependent and independent variables is linear. Okay, it can be either positively related or negatively related. Then the second one is there is no multicollinearity. Okay, the third one is residuals are normally distributed. Fourth one is homoskedasticity or no heteroskedasticity. And the last one is no autocorrelation of error. Okay, so we will see one by one what do we mean by each of these assumptions, right? So the first one talks about linear relationship. Okay, so it says the dependent and independent variables are linearly related. So what do we mean by this linear relationship, right? So if we plot the dependent against independent variables, so these are our independent variables or x's features, and this is our dependent variable, right, y. So if we plot them, so the relationship should look like this, somewhat like this. If not exactly linear, at least it should be able to be called as, okay, we can say it is a linear relationship. Okay, so either this way or it can be the other way, right? So this here is called negative relationship, negatively linearly related, and this one is called as positive related. Okay, positively linearly related. So in other terms, if our x increases, y should also either increase or decrease in some manner by some quantity, or if our x decreases, y should either decrease or increase by some quantity. Okay, if both increases, then we say that both are positively related. Okay, if both goes in opposite direction, that is if x goes upwards and y comes down, or if x goes downwards and y goes up, we call them as negatively related. Okay, so this is what we mean by linear relation between dependent and independent variables. Okay, so this is our first assumption. Now let's talk about the second assumption. Second assumption talks about no multicollinearity, right? No multicollinearity. So what do we mean by multicorrelation? Okay, so in other terms, let's consider a hypothesis for linear regression with multiple variables. Okay, I can write it as theta 0 x0 plus theta 1 x1 plus theta 2 x2 and plus theta 3 x3. Let's say that we have 3 features and our independent variable as our independent variables, and this is our hypothesis which gives our prediction or y hat. Okay, so for now we will ignore this term because x0 is always 1, right? Let's ignore theta 0 x0 for now. We will ignore. Now let us focus our view on this term, theta 1 x1 plus theta 2 x2 plus theta 3 x3. So the assumption with this hypothesis is that what this theta 1 represents. Okay, so this theta 1 represents by how much y changes with respect to change in x1. Okay, assuming x2 and x3 are constant. So if we change x1, this change to x1 is not affecting x2 and x3. Okay, so this is the basic assumption. If this is the case, then there is no multicollinearity, right? The same thing applies to other 2 variables as well, x2 and x3. So if we change x2, this change to x2 will not impact the values of x1 and x3. They will remain constant. Okay, so the same way, if we change the value of x3, this change to x3 will not impact the values of x1 and x2. They will remain constant. So if this is the case, then we will say that x1, x2, x3 are not correlated with each other. If they are not correlated with each other, then we say that there is no multicollinearity. Okay, so this is the important assumption with respect to linear regression. That is, the independent variables, what we call, or the features, are not correlated with each other. If that holds true, then we call there is no multicollinearity. So, but what happens if there is a multicollinearity? So, we will understand that. So, as you all aware, this x1 and theta 1 here, right? Theta 1 is associated with x1, theta 2 with x2, theta 3 with x3. Okay. So, what this theta 1 represents? Theta 1 represents by how much unit y changes if we change the value of x1. Okay. So, this theta 1 is purely associated with only x1. Only x1. Okay. It doesn't take into consideration about the values of x2 and x3. Okay. So, this is the important assumption. So, if there is a multicollinearity, if we change the value of x1, accordingly theta 1 should be changed, right? With help of gradient descent, we will update our theta values. Now, if this change in x1 also affects x2 and x3, this theta 1 will not be the sole indicator of the effect of x1 on y. It will be impacted by the changes of x1 also along with the changes with x2 and x3, right? Because x1 is dependent on x2 and x2 is dependent on x3. These two are in turn dependent on x1. So, if each of these terms x1, x2, x3 are dependent on each other, these coefficients theta 1, theta 2, theta 3 are not the sole indicators for the effect of those independent variables associated with them. Okay, so this is an important assumption and we need to understand this completely. If there is a multicollinearity, these theta 1, theta 2, theta 3 will not be the sole indicators of the independent variables x1, x2, x3, so that we cannot be confident on the values that we have learnt for these variables or for these coefficients or learnable parameters. Okay, so if there is a multicollinearity, these theta 1, theta 2 and theta 3 will be unstable. When I say unstable, it only means that this theta 1, theta 2, theta 3 are not the representation of the change in y, considering only x1 with respect to theta 1, considering only x2 with respect to theta 2, considering theta 3 with respect to x3. Okay. So, these things will be internally related. We cannot consider theta 1 as the coefficient associated with x1. Okay. So, that's why if there is a multicollinearity, these theta 1, theta 2, theta 3 will be unstable. We cannot rely on the values that we have learned for them. Okay. So, this is about multicollinearity. We should not be having multi-correlation between the independent variables. That's why it is called as independent variables, right? If the features are related with each other, we cannot call them as independent features, right? Or independent variables. Okay. So, this is it about multicollinearity. Next, we will talk about the third one, that is residuals are normally distributed. So, we'll see what do we mean by that. So, it says residuals are normally distributed. Correct? So, what do we mean by residuals? Residuals is nothing but the difference between prediction and actual values. Okay? So, these are our residuals. Residuals, okay? And it says residuals must be normally distributed. So, when we plot a probability distribution graph of these residuals, the shape should look like this. Okay. So, this is called as normal distribution. Normal distribution, and the shape of this is bell, right? It's a bell curve. This is also called as Gaussian distribution. Okay. If you plot a probability distribution of the residuals, the shape should look like this. Okay. If we see this particular bell curve, then we can say that residuals are normally distributed. Okay. So, this is our third assumption. Then coming to fourth assumption, it says that there is no heteroskedasticity, or in other way, we need homoskedasticity. Okay. So, what do we mean by homoskedasticity? It may be difficult for pronunciation initially, but we can split this homoskedasticity into two words. One is homo and another is skedasticity. Okay. Homo means same. Okay. Skedasticity means spread. Okay. Or in other words, we can say that variance of residuals must be almost same across the predictions. Okay. Across predictions represented by y hat. Okay. So if you plot, how we can check this? We can check this by plotting the residuals against our predictions. Okay. So if we plot this, it should look something like this. There should be a uniform distribution of the residuals across our predicted values. Okay. So you see, it is a uniform distribution. Okay. Uniform distribution, or the variance remains almost constant of the residuals across the predicted values. It should not be following any particular pattern like this. Okay. There should not be any particular pattern associated with the residuals against predicted values. Okay. It should look somewhat like this. So if it looks somewhat like this, we can say that there is no heteroskedasticity. We have homoskedasticity and our assumption holds good. Okay. So this is about the fourth assumption. Then we will come to our final and fifth assumption. It is no autocorrelation of error. So we will see what do we mean by that. So again, when we say error, it is nothing but the residuals. It says no autocorrelation. Correct? No autocorrelation of errors. So we all know, if you guys have watched my notations video, we represent the training examples with letter M, right? So we will have y as actual values, we will have m actual values, and so we will have m predictions, right? So the residuals are calculated as y hat minus y. So we will have our m residuals. These residuals are also called as errors. So we will have m errors. Correct? For each training example, we will have an associated error term. That is the predicted value for that example minus the actual value for that particular example will give us the error or residual. So it says no autocorrelation of errors. What do we mean by this? None of the y hat I minus yi, right, should be dependent on any of its predecessors or its successors. Okay. What do we mean by this? Each of the errors are independent. They are not dependent on their predecessors, the previous errors, or they are not dependent on the next coming errors. So these values must be independent with respect to themselves. They should not be related with any of the errors in the given list. Okay, so if you just plot this, if you just say in using matplotlib, if you just say plt.plot and then you just say residuals, it should give something like this. Okay, so there should not be any specific pattern, like the first error, let's say we have 2, the second error is plus 1 of the first error, that is 3, the third error is plus 2 of the first error, that is 4, the fourth error is the plus 2 of the third error, right, that is 6. So there should not be any relation between any such relation between each of the errors. Each errors should be independent. They should not be dependent on any previous or successive errors. Okay. So this is what we mean by no autocorrelation of errors. Okay. So I hope you guys understood. We have covered 5 most important assumptions with respect to linear regression. If you guys have any questions, please reach out to me via comment section. I will be happy to answer your questions. So till we see in the next video, happy learning. Bye bye.